My name's Scott, I'm here with Science Theatre, and today we're going to take a journey from the Earth to the Sun. Along the way, we're going to find out all about some of the science to do with the Sun. We're going to look at the boiling and churning surface. We're going to look at the plasma that makes it up, and we're going to look at how we could get there if we wanted to. You can see we've got a lot of demonstrations set up on the bench in front of me here. And on that note, most of these demonstrations I'm going to do today, I'd really rather you guys didn't try for yourselves. Some of these are very, very dangerous. At best, you could hurt yourself, and at worst, you could burn your house down. We don't want any of that, so I'm going to do these demonstrations so you guys don't have to. So we're going to start off on the Earth, the planet that we all live on, and of course the only planet that we know of that has lots of life on the surface. Now, to get into space, we're going to need a rocket. And let's start off by finding out just how rockets work. So I've got a little model of a rocket just here. You might say it's just a water bottle, but this will be a rocket soon enough. And there's three things we need to make a rocket work. And those three things are fuel, oxygen, and heat. Now, when we're flying into space, we have big fuel tanks. Most rockets run on something called kerosene. Sometimes they run on something called hydrogen. Of course, here on the Earth, we have lots of oxygen in the air around us. But up in space, we don't have any oxygen, and so we have to take big tanks with us in order to fly our rockets up into space. The heat source comes from igniters on the engines themselves. So let's combine those three things together, and let's see how rockets work. So we're going to need a fuel to put into this. And the fuel I've chosen here is a type of alcohol. It's called isopropyl alcohol. And it's actually the same kind of alcohol that you might find in hand sanitizer, which I'm sure some of you guys have been using quite a lot of recently. So let's pour some into the bottle here. Now, I don't want a huge amount of liquid in here. And in fact, to make sure that doesn't happen, I'm going to shake this up. So put the cap on, and I'm going to shake it up. Now, by shaking the bottle, what I'm doing is I'm evaporating the liquid. So I'm turning the liquid into a vapor or into a gas. And that's because, well, I don't want a fire in this bottle, right? I don't want burning liquid in here. So I think that's probably enough. Okay, and we're just going to pour out any excess there. So we've got our fuel, which is the alcohol vapor. We've got oxygen, it's the air in the bowl. And then we need some fire. So this lighter here is going to act as the fire. So let's see what happens. You guys at the back there might be in a bit of trouble. You guys ready? 5, 4, 3, 2, 1. So you can see that as the rocket ignited there, it pushed forwards really quickly. And that's because the fuel is burning. So the fuel burns, it produces lots of exhaust gases, they rush out backwards, and that makes the rocket rush forwards. And in principle, rockets are actually pretty straightforward. The difficult thing about rockets is making them not explode, because that's what they really, really want to do. But let's upgrade a little bit. Let's upgrade from a little bowl to a slightly bigger bowl. Now, as much as I'd love to fire this across the National Waterfront Museum here, I think I'd get in a bit of trouble if I just let this go from the stage. There's a lot of glass cases around us right now. So I'm going to leave this here on the stage, but let's see how this works. So again, like before, I'm going to take some of my fuel. I'm going to pour some of my fuel into this bowl. We're going to need a little bit more this time because this bottle's a little bit bigger. About that much. And again, just like before, we're going to shake it up to turn that liquid into a vapor. So shake that up. I never thought rockets would be so tiring. Okay. I reckon that'll do. So like before, let's pour out some of the excess liquid here. Don't worry, I'm not just pouring this onto the stage. There is a bucket behind me here. Okay, and let's just turn this lamp off to make it a little bit darker. And we're going to count down on this one as well. We all ready? Okay, let's go. 5, 4, 3, 2, 1. And you can see that if that bottle had been the other way up, it would have jumped up into the air, right? So hopefully you get the idea there of how rockets work. Basically, fuel burns, pushes the exhaust gases one way, that makes the rocket move the other way. But why do we need such a big rocket to get up into space and to get towards the sun? Well, one of those reasons is because of gravity. Now, gravity is a force that pulls us down to the Earth. And you might have noticed that every time you drop something, it always falls downwards. It never falls sideways or upwards. And a lot of people have noticed this over the years. One chap who did notice this was a guy called Isaac Newton. And in the 1600s, he realized that the force that pulls things down to the ground on Earth is the same as the force that makes the planets orbit around the sun. Now, everything that has mass has gravity. And the more mass it has, the heavier that object is, the more gravity it has. So let's say on the Earth, you could jump 1 meter up in the air. If we move to the moon is much, much smaller. Because the moon is so much smaller, its gravity is only about 1/5 of what it is on the Earth. And that means you could actually jump about 5 meters into the air, nearly high enough to get onto the roof of most houses. If you're on the sun, however, the sun is much, much bigger. And so the gravity on the sun is so strong that if you try to jump, you'd probably just fall over and end up going on fire, I imagine, on the surface of the sun as well. So let's take in our rocket, let's jump up into space. And I want to show you how gravity causes our spaceship to orbit around the Earth. Now, to do that, I have a little demonstration here to show you guys. And that involves this tray just here. Now, this used to be one of my placemats a long time ago. It's not a very nice placemat, but I drilled some holes in it and put some string on it. And this is one of the few demonstrations that you guys can actually have a go at home if you want to do that. But please do ask before you drill holes in your parents' placemats. So I'm going to take a cup just here, and we're going to pour some water into that cup. Like so. And then what I'm going to try and do is swing this plate around. Now, hopefully I've built this correctly, because on this table here, there's lots of electronics. I've got my laptop here and this odd-looking device, which we'll talk about a little bit later on. So hopefully this doesn't go wrong. Let's find out. So here's my cup full of water. I'm going to start off by swinging this back and forth. And amazingly, the water stays in the cup, and the cup stays on the tray. And I can go all the way around. And go all the way back again as well. A little bit risky. There's no tricks involved here, right? This is just science. There's no magnets holding this on. It is just a cup of water on a tray. Now, this is actually quite cool, because if you think about it, how often have you walked back from the kitchen into the lounge and maybe spilt a cup of tea or something on the way out? Well, why don't you make yourself one of these? Then you never have to. Now, this works in a similar way to how planets orbit around the sun. Basically, this string represents gravity. And as I'm spinning this round, I can feel this string pulling on the cup. And that's what's stopping all the water pouring out and falling all over the floor and all over my expensive stuff just here. So yeah, one of the few things today you can make yourselves. So do have a go at that. It is quite fun to put together. So now we're up into space. We've taken our rocket, we've launched up into space, and we can see the Earth below us. Thing is, the sun is in the sky, but it looks really, really tiny. But how big is the sun really? Thing is, the sun is much, much larger than the Earth, and so it's really difficult to show you guys just how big it really is. So in order to do this properly, I'm going to have to use a little analogy just here, a little model. So I'm going to need you guys to imagine that the Earth is about as big as this little dot on my finger just here. Now, I don't know if you guys can see that on the camera, but it's a tiny little speck. So we're going to imagine that that's the size of the Earth. Now let's imagine we take the sun, we hollow it out, and we start putting Earths into the sun. How many Earths do you think we could get inside the sun before it was full up? So imagine the sun being like a little piggy bank. You put in Earths in, you put in more and more and more in. How many Earths do you need before it's full? Well, maybe you might think, maybe like 100 Earths. There's probably 100 of those little balls in there at the moment. Actually, it's much, much more than that. You might think maybe a few thousand Earths, maybe like this. Yeah, maybe that many Earths would fill us up. No, still way, way more than that. What about a few tens of thousands of Earths? Well, I hate to break it to you, but it's even more than that. In fact, if we were to pour Earths on this side into the sun, we would need an awful lot. We'd actually need all of these, right? We'd need about 1.2 million Earths. So over 1 million Earths would fit inside the sun. To show you how many that is, let's see if we pour all these out. Hopefully without pouring them everywhere. Okay, here we go. So this is about 1.2 million once this has been filled up. That's a lot of Earths, isn't it? Yep. There we go. I reckon that's about as full as it needs to be. So next time you're trying to imagine how big the sun is, just try and remember that and how many Earths we could fit inside this little container just here. Okay. So we can fit 1.2 million Earths in the sun, but how far away is it? Because from here it looks pretty tiny. Well, let's say you wanted to drive to the sun. Let's say you get in your car and your mum and dad's driving motorway speed. Let's say we're doing 70 miles an hour. To get all the way to the sun would take about 150 years. Now, thankfully, we've got a rocket. And because we've got a rocket, we're going to be there much, much quicker. Even so, it's still going to take us a little while to get there. So while we're doing that, let's have a little chat about how the sun actually works. Why is it so hot and why is it so bright? The sun is a star. And like all stars, it's made of two gases. It's made of hydrogen and helium. Now, you might have heard of helium before. It's the one that you put in birthday balloons that makes your balloons float. It's also the one, some of you might have tried this, that if you breathe in the gas, it makes your voice go all squeaky. Now, hydrogen would actually work in the same way. So we could use hydrogen in birthday balloons, but we don't. And we don't for one very good reason, which I'll show you towards the end of this talk. For now, though, let's try and make some hydrogen. So I've got this little apparatus over here, this little set of equipment. I've got a little flask. Into this flask, I'm going to put something called sodium hydroxide. So we take a little bit of sodium hydroxide. Again, please don't try and replicate this because it is a little bit dangerous. Pour some into our flask. We're now going to add a little bit of water to this. So take my water bottle. What we want to do is dissolve the sodium hydroxide. I'm going to put about 100 mils in here, so not too much. A little bit more. Yep, that looks about right. Now we need to make sure that's all dissolved. So let's swirl this around a little bit. And we're going to use this in a reaction. It should bubble up, and we're going to make hydrogen gas. So make sure that's all dissolved. Okay. Now to make this, we need to take our sodium hydroxide and we need to react it with something else. And what we're going to react it with is aluminium foil. So I've got some little balls of aluminium foil here. What I'm going to do is put these in here, like so. We're going to put this plug in, put the bung into this beaker. That's it. And on the other end of this tube, I've connected a balloon. And as these things start to react, it should start to fill this balloon up with hydrogen gas. So this might take a little while. So I'm going to leave it there, and you guys keep an eye on that, right? So as we're going through the rest of the talk here, keep an eye on it, and eventually you should start to see that filling up. So we will come back to this a little bit later, and then towards the end of the talk, I'll show you why we don't use hydrogen in birthday balloons. Okay. So the way the sun works is a process called nuclear fusion. And what happens is we take two hydrogens, so two different types of hydrogen, and they get smashed together, and they join together to make something else called helium. Now that process where we smash hydrogens together to form helium, that also releases a little bit of energy. And that energy we can feel on Earth in the form of heat and light. Now the sun gives out enormous amounts of energy. In fact, it burns through about 600 million tons of hydrogen every single second. But it's so huge, it can keep doing that for billions of years. We think the sun's lifetime is going to be 10 billion years or so. So huge amounts of energy, far more than we could ever produce on the Earth. Now we know the sun is made of hydrogen and helium, but the sun is a very high temperature. In fact, the middle of the sun is over 15 million degrees. And because the temperature is so high, the hydrogen and helium don't exist as gases like they do on the Earth. Now you might have heard of some of the states of matter. You've probably heard of solids, liquids, and gases. Water, for example, is our hydrogen balloon. You can see it's starting to fill up there a little bit. Let's put it back in its stand. There we go. So you can see we are starting to produce some hydrogen just there. So on Earth, water exists as both solids, liquids, and gases. As a solid, we call it ice. As a liquid, we just call it water. And as a gas, we call it water vapor. And every time we do this, we're actually putting energy in. So to go from ice to water, we have to put some energy in to melt it. To go from water to water vapor, we have to put some energy in to boil it. If we keep putting energy in, though, if we put more and more energy into our substance, eventually we get something called a plasma. Now, the sun is a plasma, and fire is also a plasma. It's a fourth state of matter that you guys may not have heard of before. So I'm going to show you a few different ways in which we can make plasma. And we're going to start off by using fire and a microwave, just in case you're wondering why I've got a microwave in front of me just here. So let's move over here, walk past our hydrogen balloon, see it's doing all right. Come around here. Now again, please don't try and do this at home. At best, it could sort of damage your microwave. At worst, it could burn down your kitchen. So please don't attempt this. What I've got inside the microwave here, I've got some little stands, these are plastic stands just here. I've got a piece of blue tack in the center there, and I've got a couple of cocktail sticks. I'm just going to put these in the blue tack in the middle of the microwave just there. And let me just check that's working properly. Yep, okay. So then what I'm going to do is take my lighter, and we're going to set fire to these little cocktail sticks in here. And the reason we're going to do that is because making a plasma is quite difficult, but keeping a plasma going is a lot easier. We said before that fire is already a plasma, right? So if we make fire in here and then we add more energy to it, hopefully we can make a plasma. So let's give this a go. So use my lighter here to set fire to these cocktail sticks. Again, please don't do this at home. Okay, it's on fire. I'm going to take our bowl here and put this over the top nice and quickly. Okay, and we're going to set this microwave going. And if you look carefully, can you see a big ball of plasma forming at the top of the microwave just here? Yeah, this is why you don't want to do this at home. It also interestingly changes colour all the time as well. Let's just turn that off. Don't want to do that for too long because it gets very hot. You see it changing colour as well. Sometimes it was sort of orangey colour, sometimes it was more of a blue colour, and that's due to the different elements that are in our atmosphere. So when we get nitrogen, for example, in our atmosphere, that gives it a sort of bluish tinge sometimes. So those colours can tell us actually what the atmosphere is made out of. So yeah, that's one way of making plasma. A little bit dangerous, as I say, please don't try and replicate this. Now on our journey towards the sun, this plasma might actually cause us some trouble. And the reason why is the sun is quite a violent place. The surface of the sun has these enormous explosions, and when they happen, they send massive amounts of plasma hurtling out of space towards us on the Earth. Now on Earth, we're protected by our magnetic field. You might know that Earth is a little bit like a magnet. You can use compasses to find out which way north is. However, when this plasma from the sun hits our atmosphere, we get these beautiful green glows. And this glow is called the northern lights in the northern hemisphere, or aurora borealis. It's called aurora australis in the southern hemisphere. This picture you can see was actually taken by astronauts on the International Space Station. They're pretty safe on their spacecraft because they're inside the magnetic field of the Earth. But we're definitely not safe on our journey towards the sun. To show you the effect that plasma would have on the electronics of our spacecraft, I've got another demonstration here that I'd like to show you. So let's move our sun out of the way here. Let's try not to knock this over. Let's put this to one side. And we're going to use this thing here, which is something called a plasma ball. So we're going to turn this on. And inside here, you'll be able to see these little jets. You can see the sort of blue colours and the pink colours, and this is actually a plasma inside here. We've got a very high voltage between the middle of the ball and the outside, and that high voltage, that large amount of electricity, is causing to jump from one bit to the other, and we can see the plasma sort of lighting up while we're doing it. If I put my hand on here, you can see that electricity actually jumps through me and through my hand, through my body. Now one thing we can do here is we can use this plasma to excite various electrical equipment. Now this isn't very powerful, this is only a few thousand volts. We can still use it to, for example, light up a fluorescent tube. So if I take this tube here, put it near to the plasma ball, we can see that it lights up there. If I move my hand up, you can see that the light follows my hand up the tube there. So you can see that this is interfering with these electronics, right? So we definitely don't want big clouds of plasma going past our spaceship while we're on the way there. Another demonstration, just to show you how much it can affect electronics, is this little lamp I've got just here. I'm going to plug this in. And incredibly, I can actually control this lamp using just this plasma ball just here. So you guys ready? Kind of pretend you're like a wizard. 3, 2, 1. And we can turn it on without touching it. Let's do it again. Ready? 3, 2, 1. Make it even brighter. And one more time. 3, 2, 1. And so just using the power of this plasma and the power of this electricity, we can actually turn this lamp on without touching it. So you can see that it's definitely having a big effect, right? You can see how that might affect the electronics on our spaceship. Now, it looks like our hydrogen balloon's doing pretty well there, actually. It's getting on a little bit. I don't know if we can see that this, yeah, it's getting quite warm. This actually is something called an exothermic reaction. When we generate hydrogen like this produces heat, and this flask is getting pretty toasty at the moment. We'll give that a few more minutes, because I think that's pretty close to being done just there. So far, we've been able to make plasma from fire and from electricity through here. And now I'm going to show you the most dangerous way to make plasma. And the most dangerous way of making plasma is with a very high voltage. Now I have this crazy looking contraption in front of me just here. This is something I built at home. I think it's very unlikely you're going to be able to do this at home, but if you have any option, don't. This is extremely high voltage. It's also very high current as well, so it will kill you if you touch it. And what we've got is 2 metal poles just here, and I'm going to put thousands of volts between them, and we're going to make a plasma like the sun's made out of between these 2 metal spikes. So let's plug this in. Let's turn this on. Okay, and we can see that huge amount of electricity shooting up our Jacob's ladder just there. Looks really, really pretty. The temperature inside that arc that's going across there is thousands of degrees. It's probably about 10,000 degrees Celsius. And that's incredible, because the surface of the sun is only 5,500 degrees Celsius. So that little spark there is hotter than the surface of the sun. Let's turn that off for a moment. And we're going to short that out just to make sure that that's safe. Okay, before I can touch this. And let's move this. Let's get this out of the way a little bit. Oh, that's it. Okay, and now let's see if we can make some arcs using just this pole instead. So I'm going to make sure that's tightened up nicely. Okay, let's plug this back in. All right, so. Oh, you can see we've actually managed to control our lamp over there as well by turning this on, right? So that's another plasma controlling that over there. So if I bring this close, you can see we can actually make a beautiful arc, there we go, between the top of this and this little pole. And I say this is a plasma, it's at over 10,000 degrees Celsius and around 50 to 100,000 volts. So it's a huge, it's a huge amount of electricity going on here. So I'm just going to turn this off now. I think we've had enough fun with that. So let's turn off the power, and again, make sure I ground that, make sure that it's safe, which it is. Now, this works because the electricity between these 2 pieces of metal is so strong, it's such a high voltage, it actually makes air into a conductor. It makes air conduct electricity. And that's something we've got to be a little bit careful of. If we're flying through this plasma is going to be conducting electricity through our spacecraft, and it could certainly cause us some damage. Now, as we're getting closer to the sun, the temperature on the spacecraft is increasing very, very quickly. And here we meet something called the Parker Solar Probe. Now, the Parker Solar Probe is the closest that any spacecraft so far has got to the sun. It's still a long, long way away. It's about 14 million kilometers away from the sun as of October 2020. But when it gets the closest it's going to get, it's only going to be 7 million kilometers away. Even 7 million kilometers away, though, the temperature is pretty high. The temperature will be about 2,500 degrees Celsius. It's going to be very, very toasty. Now, any spacecraft that needs to survive that is going to need to be shielded very, very well from that temperature. And there's a couple of different ways we can do this. So to demonstrate one way, I've got a couple of bowls here on the table. Okay, let's move things out of the way a little bit. And I've got some water in this bowl. And this bowl just here, I'm going to add some of this alcohol. This was some of the stuff we used a little bit earlier. So let's pour some alcohol into that. Okay. Now, just to show you that this is alcohol, and it's going to burn very well, I'm going to take my bucket of water here. I'm going to take this piece of paper, I'm going to dip it into the alcohol. I'm going to see what happens, right? So let's dip it into there, like so. Okay, I'm going to put the lid on top just to keep the alcohol in there. Put it over our bucket. You ready? Cool. Unsurprisingly, the paper immediately bursts into flames. You can see it's all charring and going on fire. Let's put that back into the bucket there. Put that out quickly. But as you can see, that's not very useful, right? It's sort of disintegrated. Let's imagine we want to protect this piece of paper. Let's say like we want to protect our spacecraft. We want to protect it from the heat from the sun. Well, one way we could do that is to coat it in something first. And I'm going to do the same thing again now, but I'm going to try this using some money instead. Now this, you might notice, is actually an old £5 note. And the reason it's an old £5 note is because it's made of paper, not made of plastic. If I tried to do this with a newer £5 note, it was made of plastic, it would just burst into flames and melt into a puddle. So we're not going to try to do it with a newer one. I couldn't find a paper 20. So this time we're going to try and protect it first. So let's dip it into this container just here. Okay, I really hope this works. You can't get these fibers anymore. Then I'm going to dip it into the alcohol like we had earlier, like so. Bring it back over the bucket. Fingers crossed. And we're going to set fire to this. You guys ready? Okay, so it's burst into flames again, which is not ideal, but you see it's completely fine. It's actually steaming quite nicely, which is pretty cool. And the reason this works is because we managed to protect it using what was in this container here, just water. As the alcohol burns, it actually evaporates the water out of the note. This note's nearly dry, or the back is nearly dry. It evaporates the water out of the note, and that cools it down, that protects it. Spacecraft actually use this technique for landing on other planets. As a spacecraft is hurtling down through Mars's atmosphere, for example, it has a heat shield on the front, and that heat shield burns away into space, and it carries that heat away with it. So we can protect stuff by coating it and letting that burn off into space. Now I think our balloon there is pretty much done, so let's take that off. Okay. Now, this is where I try and do this without letting this go, because that'd be really annoying, wouldn't it? Okay. Let's try and tie this. Now, hydrogen does actually float, just like, or it makes balloons float, just like helium does. But I think this balloon is going to be too small to do it. Let's have a look. Oh, it's very close. Can we see that if I let go of this, it sort of falls very, very slowly, right? In fact, I wonder if I cut off this bottom bit just here. Let's try and do this without breaking it. I wonder if we can get it to float. Make it a little bit lighter. Gonna work. Cool. So now we can see that hydrogen does float. I better let that go all the way up to the ceiling. And it's only just lighter than the air. So it kind of just hangs there. It looks kind of cool. Now I said in a few minutes that I'm going to show you why we don't use hydrogen in birthday balloons. And I will show you that. Let's try and find somewhere safe to put this so that it doesn't float away. Unfortunately, I cut the little bit off the end of it. So what I'm going to do is just tape it down here. Make sure we don't lose it. Something like that. Stay. No. Cut this bit out in the edit, right? Neil, you were using me in my show. Would you like to hold this balloon for me, please? Thank you very much.
This is the balloon that's full of.
This is the balloon that's full of flammable gas. Yeah. Okay, so we'll come back to the balloon later on, and I'll show you why you don't put hydrogen in balloons, in birthday balloons. So we're now pretty much on the surface of the sun. We're about as close as we can get. And all around us, we've got these massive flares, these giant jets of plasma being shot out up into space. We've got these things called prominences, big ejections of mass up into space. We've got these loops, and we've also got sort of fire tornadoes spiraling all around us. It's pretty toasty at this point. It's pretty warm. In fact, the temperature at this point is about 5,500 degrees Celsius. Nothing man-made can survive, or natural for that matter, can survive in that temperature. I think the world record for the highest melting point of any substance is something like 4,200 degrees Celsius. So nothing that we could make could actually survive on the surface of the sun. But we can recreate some of these fire tornadoes that we see all around us. We can do that using my favorite litter bin. Got to have a favorite litter bin, right? Which is this one just here. Let's move our other flammable liquids out of the way. And this is my favorite litter bin because I can take some of my alcohol I was using earlier, pour some of that into the bin. Again, please don't try and replicate this at home. Pour some into the container in the middle. What we're going to do is we're going to try and create one of those solar tornadoes that you can see on the PowerPoint at the moment. All right, you guys ready? So let's set fire to this. We get a nice little fire in our bin. And at the moment, it's only a little fire, right? Not much going on. But if I start to spin this round, we should be able to see that this fire is going to get bigger and bigger. So let's give that a go. Okay, and as we start to spin it, we get this lovely fire tornado effect. See, the flames are getting much higher. That's pretty warm at this point. That's pretty hot. And watch, if we stop this spinning, almost immediately it dies back down again. And the reason why we get a sort of bigger flame when it spins up is because by spinning this around, we're actually adding more oxygen into the fire. When I stop this, it stops that oxygen mixing in, and then it dies back down again. We'll do that one more time. Now with this demo, the hardest thing is actually getting rid of it. Okay, so let's see if we can do that. Just give me a sec. Okay, there we go. Let's put this to one side again. All right, we are coming to the end of our talk now, but I did promise you earlier to show you why we don't put hydrogen in balloons for birthdays. So Neil, would you mind bringing the balloon back over here again for me, please? Thank you very much. I'm so glad you didn't lose it. Thank you. Now what I'm going to do is try and stick this to a little pole I've got just here. And the reason I'm going to do this is because I'm going to show you what happens when a hydrogen balloon meets a birthday candle. So make sure this is nicely taped. Stick it on the end of this pole. Like this. Okay. So let's imagine it's your birthday. You're sat down, you've got the cake in front of you. Somebody comes over, lights the candle, and everybody's singing happy birthday to you. Let's move this out of the way. Somebody brings over your birthday balloon. Something like this. Your birthday balloon gets a little bit too close to the candle. Let's see what happens. And that is why we don't put hydrogen in birthday balloons. Okay, thank you guys very much. Cheers.